Stability is the second measure. This is the most important actually criteria or measure for the analysis. Why? Because like if your system is unstable, then it doesn't matter like what your transient response is or what your steady state response is. Okay, because the system itself is unstable. So for an unstable system will not give you an output that you are actually desiring. Okay, for example, if you want to have the 25 degrees Celsius from your thermostat or from your heating unit, okay, but your system is not stable there, it's not controlling the temperature there. So it doesn't matter if you give it the input command as 25 degrees Celsius or 20 degrees Celsius. The system will like keep on, maybe is if it is on, like it may go beyond 25 degrees Celsius to 30, 35, 40, and maybe it keep on increasing. Okay, so it means that your system is unstable. So if the system is unstable, all other parameters, all other controls, things are are useless. So stability is one of the most important criteria. Okay, so how actually you can define your stability? So stability can be defined like differently based on what kind of system are you using or what point of view are actually you looking at your system. Okay, so let's first define the stability based on the natural response. So what is a natural response? If you just recall your previous lectures, we said that consider an LTI system. Okay, what kind of responses, total response is there? We said that this combination or the sum of two responses are forced response and the natural response. All right, the forced response is due to the input. Whatever we are giving in is an input, like it's a step response, or it is the ramp response, or any other response, maybe a sinusoid if you are giving it as an input. Okay, so the response due to the input is called the forced response. The natural response is then due to the inherited characteristic of the system. All right, so what is the natural response of the system? Okay, so it is a combination of these two, if you remember from your previous lectures. Okay, so basically a system, or whatever we are actually interested in controlling our system. Okay, it could be either stable or it could be unstable, or it is another category which we call the marginally stable. So your system must be in one of these three states. Either it would be stable or unstable or maybe marginally stable. So what does a stable system means? A stable system in an LTI system means that if your natural response approaches zero as time approaches infinity. What does it mean? Like, with the passage of time, your natural response or your system, like it comes down to one specific, or it comes down to an equilibrium, or you can say that it comes down to the final value that is associated with that system. All right, for example, like if you don't give any input and your temperature in your room, like it should be, let's say 20 degrees Celsius. Okay, so if it is staying on that over a period of time, it means that your system is stable. But like if without giving any input and your system temperature is increasing, it's more than that, is increasing up there, it means your system is unstable. If your natural response grows without any bound, as the time approaches infinity, which means that after the passage of certain time, if your system is not stable, like if your natural response is still growing, it means your system is unstable. Okay, and the third thing is that, like time variant is that marginally stable. If the system natural response neither grows nor decays, it means that for that system, your system may be marginally stable. So that's the definition of the stability from from the perspective of natural response. But there are some issues. For example, just it is somehow difficult to, for example, if your system is unstable, like and if you're looking at the total response, you are unsure that whether the system is unstable because of the natural response or maybe because of the total response, or the forced response. Sometimes you are unsure about it. Okay, while defining this this stability. Okay, For example, like if the input is bounded and the total response is not approaching infinity as the time. Okay. If the input is bounded and the total response is not approaching infinity as the time approaches infinity, then natural response is obviously not approaching infinity. What does it mean? I mean, like if you give some input which is actually bounded or which is controlled or which is in the limits, okay, and your total response is not approaching infinity, okay, then what does it mean? That your natural response is, I mean, like your system is stable, okay, your input is stable and your output is also stable, okay. But what does it mean there? Whether your natural response is, stable, your system is stable due to the natural, from natural response perspective. Uh, you can say yes, because since the overall system is stable right here. But if the input is unbounded, for example, and we see the unbounded total response, we cannot arrive at a conclusion about the stability of the system, okay. For example, if you are giving the input which itself is problematic, okay, which is not bounded or which is not within the limits, okay, and your system output response is also okay, and your output response is also not what is that, and your output response is also unstable, okay. So if your input is not stable or which is not in the limits, so obviously your output, if your system is response is not stable either, or not within the limits, it means you can say that there isn't any stability in your system. But you cannot say that, from, if you're just looking at the definition of natural response, you cannot say that whether this stability is due to the natural response or due to the forced response. All right, that's why actually we have to consider the overall response, which